Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your channel Chandan Physics. In this video, we are going to discuss mutual induction and reciprocity theorem in mutual induction. Let's begin. Mutual induction is the phenomenon of production of induced EMF in one coil due to the change of current in a neighboring coil. Let us take two coils. One coil named as P, another coil named as S. The coil P, called primary coil, that is primary coil, and the coil S is said to be secondary coil. That primary coil is connected through the battery through a key K. This is the key K. The secondary coil S, which is known as the secondary coil, that is connected to a sensitive galvanometer. G. Look here, when the key K is just pressed, what happened? The primary circuit, an EMF is induced in the secondary circuit, and the galvanometer records a deflection when the current in the primary coil attains the maximum value. Then the induced EMF in the secondary coil vanishes and the galvanometer does not show any deflection. Now, on releasing the key, again the current in the primary starts decreasing from maximum to 0. At that case, the EMF is again induced in the secondary, but in opposite direction. That is why the coil P and S are said to as pair of coils, or we can say the coupled coils. Okay. Look here, when current key on, current through that of primary coil, that current produces the magnetic field lines. Here inside the coil there will be the magnetic field lines. Also, the magnetic field lines through the coil S due to the current in primary coil. Due to the change in magnetic flux, in secondary coil, an EMF is induced. That's why the current generates. So what we look at that particular scenario, the magnetic flux linked with the secondary coil is directly proportional to the current flowing the primary coil. The primary coil, that is phi s magnetic flux linked with the secondary coil, that is phi s, the total magnetic flux linked with the secondary coil, is directly proportional to the current flowing through that of primary coil, I p, current flowing through that of primary coil. So here the terms are phi s is the total magnetic flux linked with the secondary coil, and IP is the current flowing across primary coil, current flowing across primary coil. Now we use the proportionality constant. To remove that proportionality, we use a constant which is the phi s is equal to m I p, where m is known as the coefficient of mutual induction, coefficient of mutual induction or mutual inductance, coefficient of mutual induction or mutual inductance of the coil. So we define what is mutual inductance. Mutual inductance can be defined as, hence the coefficient of mutual induction of two coil is defined as the magnetic flux link linked with one coil when a unit current unit current passes through the neighbor coil, passes through the neighbor coil. Okay, that is the coefficient of mutual induction or mutual inductance. Now, we can use Faraday's second law of electromagnetic induction from Faraday's law of electromagnetic induction the induced EMF in secondary coil, that is ES, is equal to minus d phi s by dt, rate of change of magnetic flux. In place of phi s, we can substitute MIP or ES is equal to minus d by dt MIP or ES is equal to minus M d IP by dt. Here the negative sign refers the direction of induced EMF, is opposite to the current of primary coil. To the current of primary coil. That is the reason we introduce negative sign here. Now, the coefficient of mutual induction or mutual inductance of the coil, the unit here, the unit in SI is Henry. Let me define 1 Henry. When dip by dt is equal to 1, then ES is equal to minus M. In this way we define definition of 1 Henry. How we define 1 Henry? 1 Henry is the mutual inductance of two coils when a current changing at the rate of 1 ampere per second, in one coil of primary, one coil induces an EMF that induces an EMF of 1 volt in the neighboring coil. In the neighboring coil. Okay. So, the value of mutual inductance depends upon various factors. Mutual inductance depends on various factors. Look the factors one by one. First one, be the geometry of two coils. Geometry of two coils. Geometry in the sense that is the shape, size and number of turns of the coils, of the two coils. And the relative placement and orientation of the two coils. The relative placement and orientation of two coils. Next point, the nature of material. Nature of material of the core of the coil. Which they are wound. Next, the separation between two coils. Separation between two coils. These are the factors on which mutual inductance depends. Separation between two coils, the nature of the material used in that of core, and the shape, size of these two coils, shape, size and number of turns of the coils, and again the relative placement or orientation, how the primary and secondary coils are placed to each other. Here a point is to be remembered, that in case of mutual induction, exactly what happened when current is induced in the secondary due to the mutual induction, then simultaneously an EMF is also induced in the primary coil. Hence, the self induction and mutual induction both are occur simultaneously due to the induced current in that of primary, that is the self induction process. So, here in case of total mutual inductance process, both primary coil and secondary coils, here self inductance and here mutual inductance, self induction and mutual induction occur simultaneously. Okay. In this way, we define the process of mutual induction. Now, reciprocity theorem in mutual induction. Reciprocity theorem in mutual induction. How to prove that reciprocity theorem? Look here, consider two circuits. Here we consider a circuit. There will be the another circuit. These two circuits are placed very close to each other, such that I1 amount of current flows flows that of loop C1. That circuit is named as C1, that loop is named as C2. Here I1 amount of current passes through that of circuit, I1 amount of current passes through that of circuit C1 due to the battery. Now we consider a point P. Here we take the point P. At any point in the circuit C2, having the position vector, let R1 be the position vector of that point P away from the current element. Let we choose a current element here, the current element, that current element be I1 dL1, dL1 be the length of that loop section. The position vector of that point P from this current element is R1, is R vector, position vector of that point P. Now due to that current element, a magnetic field is produced of that of circuit at point P. Here we calculate the magnetic field at point P due to that current element by using Biot-Savart's law. By using Biot-Savart's law, Biot-Savart's law, the magnetic field produced, by current element I1 dL1, current element of the circuit at point P. That is dB due to this small current element, K I1 dL1 cross R vector divided by RQ. Here K is equal to mu naught by 4 pi in SI system of international unit. This is the magnetic field intensity at point P due to the current element, that of circuit C1. Now the net magnetic field produced by the circuit C1 at point P. Therefore, the net magnetic field produced at point P by the circuit C1, is B is equal to K closed curve integration over C1 I1 dL1 cross R divided by RQ. That is the I1 into dl1, I1 into dl1. This is the current element vector. And the net magnetic field at point P due to that circuit C1. Now, let the expression for magnetic flux linked with that circuit C2 what will be the magnetic flux? There will be the magnetic field intensity at point P, there will be the magnetic field lines. So, magnetic flux linked with the circuit C2, magnetic flux linked with the circuit C2 is phi 2. Magnetic flux linked with the circuit C2 is phi 2, which is equal to the surface integral, means the area integral. Here we choose the surface element as dA2, small surface from that of circuit C2. Area integration magnetic field dot product with that area. This is the flux linked with that of circuit C2, where A2 is the area enclosing the area of surface enclosed by the circuit C2, by the circuit C2. Now, we substitute the value of B here. Phi 2 is equal to K surface integral, the value of B as line integral closed curve integral C1 I1 dl1 cross r vector divided by rq dot dA2 vector. Which is equal to K I1 A2 C1 D L1 cross r vector RQ at dA2. This for phi 2. Here we use the concept as we know that gradient of, here I use grad 2, not confused, grad 2 for that of circuit C2. For our convenient I use grad 2, means that refer to gradient of one by r is equal to minus r vector divided by rq. That reference is used here, or phi 2 is equal to minus k I1 A2 C1 D L1 cross grad 2 1 by R dot D A2. Okay, look here. In case of vector product, these are not commutative, means A cross B is the negative of B cross A. In that scenario, we use as A cross B is equal to negative of B cross A. That's why the negative sign can be written as K I1 A2 C1. Here I change its position, grad 2 1 by R cross D L1 dot D A2. Again use the vector identity. Here use the vector identity, gradient of phi A. Phi is a scalar function, A be the vector. In that way, in that of case, grad cross phi A, grad cross phi A is equal to phi grad cross A plus grad phi cross A. That identity is put here. Here phi is equal to 1 by R, A vector is equal to dl1, and grad is termed as grad 2. That identity is used here. We write phi 2 is equal to look here how exactly we found the term. Look here what exactly the terms are found here. Therefore, grad of phi A, so grad 2 cross D L1 by R is equal to 1 by R grad 2 cross dl1 plus grad 2 1 by R cross dl1. Look here, grad 2 is not a function of x1 y1 z1, as we prefer that for circuit C2, for circuit C1 the coordinate may be in terms of x1 y1 z1, for in circuit C2 the coordinates in terms of x2 y2 and z2. Here grad 2 is not a function of x1 y1 z1. Therefore, grad 2 cross dl1, that will be 0, grad 2 cross dl1. Why? As grad 2 is not a function of x1 y1 z1. That's the reason that cross product of grad 2 cross dl1 vector will be 0. Therefore, what we find here, grad 2 cross dl1 by R is equal to, here we found grad 2 1 by R cross dl1. That result is putted for that given equation. So, phi 2 is equal to k I2 surface integral A2 closed curve integral C1 grad 2 cross dl1 by R dl1 by R, the cross product result here. Dot d a2. Okay. Now that can be written as phi 2 k I2, that integral is written as closed curve integral C1 the surface integral A2 grad 2 cross dl1 by R dot d a2. Now using the Stokes theorem, if I use Stokes theorem, then that surface integral is changed to line integral. So, using Stokes theorem, so the area integral A grad 2 cross dl1 by R dot d a2, that is the surface integral. That surface integral particularly changed to line integral. So, the line integral, that is the closed circuit C2, that will be d L1 dot the line integral term d L to surface integral changed to line integral R. Now, using the Stokes theorem here, that surface integral converted to line integral. Therefore, we have our phi 2 is equal to k here are I1, these are I1, current I1 that is closed curve integration C1 closed curve integration C2 d L1 dot d L2 divided by R. Now, that equation can be compared with the expression for magnetic flux in terms of mutual inductance and current. That is why that phi 2 is written as M21, that is k I1 sorry not I1, that is the result of M21, that is the expression for C1, expression for C2 dl1 dl2 divided by R. Look here, the expression for mutual inductance, that is the magnetic flux M is equal to di by dt. Magnetic flux is equal to mutual inductance into current, that expression is correct. So, in place of I1 phi I1 I can substitute M21, M21 here, M21 is the mutual inductance of circuit C2 with respect to circuit C1. That is the mutual inductance M21 here, M21 mutual inductance of circuit C2 with respect to circuit C1. So, here the mutual inductance depends on the sizes, shapes and the relative positions and orientation of these two coils. Again, if we interchange its position, again if we interchange the position means M12 mutual inductance of 1 with respect to 2, that expression is written as K closed curve integration over C1 closed curve integration over C2 dL2 dot dL1 divided by R. These two are equal. Equation number 1 and equation number 2, M21 is equal to M12 from 1 and 2, from 1 and 2 M21 is equal to M12. Mutual inductance of circuit 2 with respect to circuit 1 is equal to mutual inductance of circuit 1 with respect to circuit 2. That result is known as reciprocity theorem of mutual inductance. That is reciprocity theorem of mutual inductance. According to that theorem, the coefficient of mutual induction remains same irrespective of the fact that current is passed through coil C1 or through C2. Either current pass through C1, either current pass through or current pass through C2, but there will be no such change of mutual inductance. That particular theorem indicates that point. So, with the help of this video lecture, we understand the concept of mutual induction, reciprocity theorem in mutual induction. We take two circuits, these are the situations where these things are pointed to this, that particular these are the way why exactly that equation changed. These are the reasons why that equation reduced like this, then M21 and M12. That is the reciprocity theorem of mutual inductance. So, with this useful and informative notes, let me wind up this session. Thank you.